Tá? Bom, boa tarde a todos, sejam bem-vindos à série de seminários de computação. O palestrante de hoje é o Guilherme Ottoni. O Guilherme é Distinguished Software Engineer na Meta, Estados Unidos. Ele é filho da casa, né? Fez mestrado aqui na Unicamp, depois doutorado dele em Princeton, teve uma passagem na Intel. E estava com quanto tempo na Meta, você?
11 anos.
11 anos. Fez contribuições significativas lá, de otimização de código lá na Meta, que é isso que ele vai contar essa história para a gente hoje. Seja bem-vindo, Guilherme.
Tá bom. Obrigado, Guido. Obrigado, pessoal, por vir aí. É um prazer estar de volta aí na Unicamp. Já fazem 20 anos que eu saí daqui, mas ainda tenho ótimas memórias dos anos que eu passei aqui. Essa palestra eu vou fazer em inglês, porque acaba ficando meio confuso, acaba falando metade de português, metade de inglês, então eu vou fazer em inglês, mas fica à vontade para perguntar qualquer coisa em português. Okay, so the title of my talk is The Evolution of PHP and Hack Execution at Meta. So this is basically a summary of a lot of the work I've been doing there for the past 11, almost 12 years. And yeah, that's what I'm talking about. So let me start motivating why PHP. I don't care about the execution of PHP, because it turns out PHP is a language that's not very well regarded. A lot of people think it's poorly designed, and it does have its own quirks. It's a language that evolved quite a lot over many decades at this point. And there's a lot of things that we've been trying to fix in the language with a dialect that we developed at Meta that we call hack. And I'm going to talk more about this later. But the main point I want to make here is that despite its quirks, PHP actually is a very successful language. And interestingly, I think the reasons why it became popular is not because of the language itself, but because of two main features. The first one is the integration that it had with web servers very early on, like Apache, that allowed very easily to develop web applications on top of it. And the second one is that it enables a very rapid development cycle. So if you are writing even a very large application with millions of lines of code in PHP, it's very common for developers who save the change in their code in the text editor and switch to a browser and just reload and almost instantly see the effect of their change. So that enables a very rapid development cycle that people really appreciate. And to further illustrate how popular PHP has become, I pulled a list of top websites as of last week based on how much traffic they drive. And it turns out that 7 of the 10 top websites actually are written at least to a good extent in PHP or the hack dialect of PHP. And this varies from websites to do social media, search, encyclopedias, news, and even some adult content as well. So it's pretty popular for very different uses. And if you're running a website that drives a lot of traffic and you have a lot of users, you probably care about the performance of your application. To give you guys an idea, in case of Meta, we build and operate our own data centers. And this picture shows one building in one of our data centers. And it's hard to have a good idea of the scale here, but one of these buildings is about the size of 4 football or soccer fields. And each data center has several of these buildings, and we have about 20 data centers spread around the globe. And inside these data centers, we have racks of piles of servers, and a good chunk of those are running PHP or hack code. And unfortunately, PHP is a scripting language, and the only implementation that's really existed before is a very simple interpreter. So that became a problem very early on for Meta, or still called Facebook at the time, because having a very large number of servers running a language that's not very efficient, we thought we could do something better. So our first solution to that was to build what is called the hip-hop compiler, which was a very high-level source-to-source compiler that translated PHP code into C++. It was a very simple compiler that only built one intermediate representation, an abstract syntax tree, and did some optimizations at that level. And one of the main things it did was to do type inference, trying to infer types of things, because if you know the types, then you can compile code better. It's often hard to do that for a dynamic language. And for example, if you're concatenating two strings, you know that the result's going to be a string. But say if you're dividing two integers in PHP, now you don't know because it can be an integer, it can be a floating point, it can even be a boolean, surprisingly. But it can happen. So then these things make it very hard to compile. And there's a lot of, so we used to translate PHP to C++ and then just use GCC in the backend to compile this to actual machine code. And there's a lot of interesting challenges and techniques that we came up with to build that compiler and be able to compile a very dynamic language into a static language, but I'm not going to talk much about that. And we have a paper, Noops, 10 years ago now that talks in a lot of details about these challenges. But here's a graph showing the impact that that project had at the company. And it's a graph showing the performance relative to running PHP, the Facebook website at the time, we did in PHP, and we switched to using hip hop in the beginning of 2010, and at the time that was a 2x speed up, so it reduced the number of servers we needed by half. So it was pretty significant, and we kept improving it over time, and over the course of the life of that project, over 3 years, we made it about 6 times faster than running the website with standard PHP. And one caveat here in this graph is that there's a lot of things that are changing. It's not very accurate. We could actually only run the website using the standard PHP up to some point in late 2010. And at that point, because we control the compiler, the language, we started adding features that standard PHP didn't have. And once we started using that in our website, then we couldn't run on top of PHP anymore. So after that point, the speedups here were basically measured by, with every release of the compiler, we measure the performance versus the old one and kind of aggregate that over time. And of course, also the application was changing at the same time, and new hardware was being deployed, so a lot of things were changing, but this gives an idea of the magnitude of the wins that we had. And despite being very successful, there were a few important drawbacks with the hip hop compiler. The first one is that it was pretty slow compared to running with an interpreter for development. So, as I mentioned, a key feature of PHP is that you just save your code and reload the browser and see the effect. Here, we started put this compiler translated to C++ and using GCC, and that made the build take 15 minutes, even using a cluster of servers to do parallel compilation. So that kind of broke this fast development cycle, and our solution to that was to keep using an interpreter for development, but then having this compiler just for production. But of course, having two different implementations of the language over time, we kept hitting different subtle difference in behaviors or bugs here and there that caused trouble to us. And that was one of the problems. Another problem is that the binary that was generated was also getting very large. At the time, the Facebook website had about 30 million lines of code. Compiling that to C++ and then generating this binary, we ended up often starting to hit the limit of 2 gigabytes that we have for a text section on Linux. And that, for the last year of life of this project, we are hitting that limit very often and having to play a lot of tricks to accommodate that. And first and last, the main drawback of this compiler was that it was basically just relying on static analysis to try to infer types. But once you can't infer types, you have to do very inefficient codes to dispatch every operation based on the types of inputs, checking if you're dealing with integers, strings, or arrays, or objects. And that was very inefficient. And there was no way to easily accommodate using profile information from one-time execution to feed back to this compiler, unless you made it even way slower to compile, things like that. So these reasons motivated us to create another compiler that or a virtual machine that we call Hip Hop VM or HHVM, which we use some of the same components we had built for the Hip Hop compiler in the front end, but instead of emitting C++ code, we emitted a bytecode representation that we call HHVC. It's a custom bytecode that we created. And so ahead of time, we've compiled and generated this bytecode, and now we deploy that bytecode to the servers running at runtime. And at runtime, we start running that bytecode and compile that to machine code, going through a couple of different intermediate representations and doing optimizations there with a just-in-time compiler. So the basic principles that we use in the first generation of this just-in-time compiler that we built is that we wanted to be able to leverage dynamic type specialization and compile the code for the types that were actually being observed during the execution. So we basically observe the types that you're seeing, compile code for that, and insert some checks to make sure that you see those types next time they come around, you have the code already compiled for that, otherwise you can create specialized code for different combinations of input types. And a key concept here is what we call a tracelet, which is basically a maximal sequence of bytecode instructions that we could compile to machine code in a type-specialized manner just by inspecting the live types of the variables of the state of the virtual machines, what the variables had at that point in time. So I'm going to illustrate that. So here's a very small piece of PHP code that does a division, stores the result in a variable, and then checks if that's greater or 0, and then breaks somewhere. So this piece of code would be broken into tracelets that I'm representing here by the bytecode instructions, but it doesn't really matter what they are doing there. But this is just to illustrate how things work. And we will do the division in this case, and the result of the division, as I mentioned in PHP, even if you're doing it with integers, it may not be an integer. So we'll have to break a tracelet at that point, executes the code, and now you can observe what the result was, and then you specialize the code for that result and keep going. And once you reach a conditional also, you don't know which way you're going to branch, so you generate code up to that branch, and now you execute the code up there, and now you figure out which way you go, and then you compile code for the branch that is actually taken during the execution. And each of these tracelets, we generate code following this pattern where we do some type checks in the beginning to check what are the types of the inputs that you're going to deal with in there. And assuming they pass those checks, now you have very efficient machine code that you emit specialized for those types. And if the types fail, you jump back into the runtime to recompile code for different combinations of types that you are seeing now. So here's just a basic overview of the architecture of the compiler. It's basically inspecting a lot of the VM states, look at the bytecode that was recompiled ahead of time, and generate machine code going through a more or less standard just-in-time compiler, doing a bunch of optimizations all the way to generate the machine code. So here's a bit bigger example of how tracelet compilation works. And this is a small example that has a loop that goes over an array of elements and adding up computing the average of the positive elements in the array. So this piece of code, just looking at the body of the loop, it will be split into multiple tracelets. You start executing the loop body here by loading the array elements, and now you stop because you don't know what the element is going to be. And now you generate code that processes that element, and you can specialize, okay, that element was an integer or something. And now you execute that code up to the point where you do that check if the element is greater than 0, and then you stop because you don't know which way to go. So you generate another tracelet to handle, okay, I took that branch, so I'm going to add the elements, and so on. And then you do the loop increment and loop back to the beginning. Right? So, and if you keep executing and say your array has a combination of integers and doubles, sometimes you're going to fail some of these checks because you see a different combination of types, and you go and rejig another piece of code to handle the other combination of types, and you chain all of these, so each time you get to that piece of code, you check which translation matches your types, and if none, you may generate another one. So tracelets were a very simple and good abstraction that we came up with that has the advantage of being able to specialize the code for the types that we execute at runtime, that we see at runtime, without having to do a separate profiling pass to obtain type information. And it also has the advantage that you only compile the code that actually executes. And if you have a very large function, you only execute the beginning of it and you return immediately. You don't spend time and overhead compiling the entire method. However, it has some drawbacks. So the fact that we break the program into very small compilation units, that prevents doing optimizations that go across compilation units, right? And also, this is a simple way to specialize the code, but it doesn't provide us a way to do more general profile-guided optimizations that are usually very useful for compilers in general. And for dynamic compilers, for dynamic languages, it's even more important because there's so much dynamic behavior that you can learn and specialize the code for. So those reasons motivated us to build a second generation of the just-in-time compiler inside HHVM, which follows these principles here. The first is type specialization, which we had in the first version of the JIT and was very useful. We also use a lot of side exits using this technique called on-stack replacement, which already had also, which is basically at every byte code instruction boundary, you have the ability to stop execution. You can generate more code, or you can fall back to an interpreter, and so on. So you can basically switch between different execution engines at every byte code instruction boundary. And we add on top of that profile-guided optimizations and a mechanism using region-based compilation that I'm going to illustrate. So the basic architecture of the JIT in blue is what we had before, and we kept that mode of execution by just inspecting the live state of the machine, of the virtual machine to generate code. But for at least the hot portions of the code, we want to do a step of profiling the code and re-optimizing it. So then, if we're profiling, we take this intermediate row here, which basically is similar to just the tracelet compilation, except that we insert profiling counters in the codes to learn and profile whatever behavior you want, like type information, but also targets of dynamic method dispatch and so on. And then we execute the code with those profiling probes for a little bit and to learn, gather enough information and save these in some profile data. And later we can go and generate code using this profile data to form larger regions of code and do more aggressive optimizations. So going back to the example we had before, say we basically, during profiling, we generate similar code that we had before with the tracelet JIT, except that we had profile counters there that are going to tell us, okay, these are the hot blocks that are executing, and now you can come back and regenerate that code by saying, okay, I'm going to form a region only with these blocks, but now I'll compile this whole thing as a unit, and now I can do more aggressive optimizations. For example, hoisting looping inherent code outside of the loop, something that you couldn't do with a simple tracelet JIT. So here's a continuation of that graph showing the performance that we obtained with the system. Around here, January 2013 is when we switched from the hip hop compiler to using HHVM in production. And since then, we kept improving performance quite a bit by doing a lot of these things that I talked about, doing a lot of profile-guided optimizations, region-based compilation, and a lot of other tricks that we played. And to give you an idea, the performance speed up today is something nearly 80 times faster than what we had before, with the same caveats that we had before, right? The application changed dramatically, there's new hardware, and we couldn't run the code with the standard PHP anymore. But this is kind of just accumulating the wins by measuring the impact of every release of the compiler. And so those techniques worked well, and especially in the beginning when we started HHVM. But we also made the JIT a lot more expensive by doing this profiling, and these things became a bigger overhead over time for a combination of factors. And first, the size of the code base that we're compiling kept growing over time, and today is in the hundreds of millions of lines of code. So that's more code to be compiled and be optimized. And we also, when we deployed HHVM in the beginning, we had, I think we were updating the site once a day, or maybe not even that, every other day. And if you're updating, say, the website once a day and redeploying HHVM and compiling the code and then keep running for 24 hours, then that's okay. But over time, to enable the programmers developing the website to iterate more quickly, we started deploying the site, okay, 3 times a day, 5 times a day. Eventually, we moved to a continuous deployment where it's fully automated, and assuming all the tests pass, the new version of the website just rolls out continuously. And today it takes about an hour and 15 minutes for the new version to come out. So because of that, this overhead of compiling the code now was not amortized over 24 hours, it was only over 75 minutes, and these overheads became bigger and more important to address. And now if you compound these overheads across a very large fleet of servers, it's a lot of CPU time that was being spent just warming up the virtual machine, just to throw all of that away and restart again in the next hour. And as I mentioned before, we were going basically through these steps of, okay, we start at the end, you start taking requests, compile them, profile the code, running the profiling code for some time, recompiling, and to give you an idea of how slow the server would come up. So here's a graph that shows the relative throughput of the server. 100% would be if you are running, you compiled all the code you were willing to compile, or running at full speed, and the red line shows the relative performance of that in the first 10 minutes of the lifetime of a server. And it was very slow in the beginning as you're profiling, compiling code, all of these things taking place. And it took about 10 minutes to reach close to 90% of the maximum throughputs that we could achieve. And so 10 minutes out of 75 became significant, and we decided, okay, how can we optimize this? So to solve this problem, we came up with a technique that we call jumpstart, that builds on previous work that people had done on Java to try to reuse profile data from one execution of the virtual machine to the next one. The problem for us is a bit different because from one execution to the next one, the application has thousands of changes in the code. So we couldn't really leverage much safely the profile information from one run to the other because the code changed quite a bit. And so what we did was to basically leverage the staged deployment that we already had for the website. So if you're running a very large website like this with a very large number of servers, you don't restart them all at the same time. So what we do is, we first restart for 2% of the fleet, and we run that for about half an hour, watching a bunch of automated tools that are checking everything that can possibly go wrong and try to detect that it's safe and stable enough so we can roll that out to the rest of the fleet. So what we did was to use those first 2% of the servers to actually collect profile data, and then we distribute that to the other servers so that when the rest of the fleet is about to come up, it doesn't have to JIT code in profiling mode and collect the profile data. It already has that available and can JIT the code in optimized mode right from the start. And you can do that even before you start taking any user requests, because you don't need to run any code. You have the profile data. So that doesn't affect warm-up and doesn't cause even spikes in latency that users could see in the beginning. So here's a chart showing the impact of this technique. So red is the line that we had before showing the warm-up, and blue is what we had with jumpstart. And you can see that the request per second, or the throughput, goes up much more quickly. And we're basically compiling the code in the first minute or two here. And then once we start taking user requests, the line goes up much more quickly. And this saved about 55% of the capacity that we're losing with every web push or every time we're restarting, updating the website. So I mentioned that's what talked a lot about performance, but I mentioned also that we have this dialect of PHP that we call hack. And so this is, once we control the whole stack, the whole language implementation, we decide, okay, let's try to improve the language to make it suit better our users and make sure that we get rid of things that are dangerous and cause problems often. So we start to evolve the language on our way, kind of fork from PHP at this point. And so we added a lot of things like async function execution, memorization. You can annotate that function. Okay, you can memorize this function. So if you call a function multiple times with the same arguments, it's going to just return the result from the previous execution, and you don't have to do that manually. You just put an annotation of function, things like that. And we have a very powerful static type checker that can type check the millions of lines of code very quickly and point typing errors that you may have accidentally done. And the language has a gradual typing system so that you can slowly annotate and add more type information, but you don't have to do everything in one time, which is very useful for a very large application. And the challenge here is that we're doing this all at the same time. We're updating the language, adding features, or sometimes removing features. But doing that as we're updating this application that has hundreds of millions of lines of code, and trying to do that and updating the runtime, the virtual machine as well, all of that while the site is running and trying not to bring things down. So that's kind of the challenge that we have. And, but this also brought more opportunities for us to do optimizations and improve performance even further. So as I mentioned, like AC function execution, memorization are things that enable us to get performance improvements. And there are features in the language that also were hard to optimize, and we had to customize a lot of optimizations because of them that were not super useful, and we eliminated, like PHP references or destructors and other things. Okay, now I'm going to switch gears a little bit and talk about some lower level optimizations, or at the binary level that we did, primarily motivated by HHVM, but this turned out to be useful more generally. And the first one was we observed that the GCC compiler was doing a very bad job by placing functions that one called the other very far in the binary, and that caused a lot of instruction TLB, instruction cache misses that we thought we could avoid. So we built a tool called HFSort for hot function sorting, which is actually something that we hacked, me and two other colleagues in a week. That turned out to be very impactful. And it doesn't require instrumenting the code or anything. Basically, you run the application as you're running. You collect just profile samples, looking at stack traces with Linux perf tool. And by inspecting the stack traces, you know what function called the other. And we use that to build, we built this tool that takes these stack traces and builds a dynamic call graph, so knows, okay, which function calls another one more often. And now we apply a graph clustering algorithm, and we generate a list of functions that we think this is ideal order that we should place them in the binary. And we compile the functions with an option to put each function in a different section. The linker doesn't know functions, only sections. So we encode, okay, these are the sections that we should put, and then we just relink the binary and get the linker to place them in the order that we want. So this was very simple hack that saved about 8% of the servers for HHVM. And then we figured, okay, and this is kind of general, and we saw the same problems in other services at the company. So we ended up applying this to basically every large-scale binary that we have at the company, saving a similar number of servers as well. And this optimization today is actually also implemented in the LOD linker. And it's actually a funny story because someone working on the LOD linker read our paper, and he actually was a student here at the same time I was, and he reached out to me, oh, I see you wrote this paper, and he was my student in the ACM team that I used to coach here, and he implemented this, he and a colleague implemented in the LOD linker, and it actually implements this optimization also natively, so you don't need to do this hack using a linker script that we initially did. So that took care of reordering the functions in the binary, but we also saw opportunities to improve the layout of each function and reordering basically the basic blocks of functions. And we thought about trying to do that, but it's hard to do that with you can do this with a linker only, and it can move only sections, which are functions around, but not go inside functions and mess up with them. And we thought, okay, we can build something like that using the LVM compiler infrastructure, but this is going to be harder to do. It's not something I'm going to be able to hack for a week. And so to solve that, we hired a couple of interns to do it. And one of them, Rafael Auler, actually from Unicamp, came and did an internship with us when we were starting this project. And this turned out to be very useful as well. And basically the tool takes a binary that's already linked, takes profile data that we collect just with hardware sampling also, takes that binary apart, reorders the blocks inside the functions. Today, it reorders the functions also using the same technique that we had before from the HFSort tool that I mentioned, and puts the binary back together, and it's just a more performance version of that same binary. And This saved us about 6% of the CPU or servers on top of HF sorts that we had before. And here's a chart showing the effect of that at runtime. So this is basically a 2D view of the binary address space. Look at the text code. And if you just compile the code without profile information, here shows a heat map where we're spending the cycles, and you can see it's all over the place in the binary. And if you use compiler to do profile guide optimizations and code layout, it does a decent job, improves a little bit like this. But if you use this tool that we built, both, then you get a much more compact code. And that's why it improves a lot the code locality and saves a lot of instruction cache miss, even branch misses like you'll be missing and so on. And yeah, so that's basically a summary for what I had. So just to conclude, I think there's a lot of opportunities to do compiler work out there that's very interesting and challenging. And it can be actually very impactful, especially for very large scale applications. And some of the tools that I talk about and techniques that we built include the hip-hop virtual machine, the hack programming language that we're forking from PHP, HF sort tool. They're all available in the Facebook GitHub. And the both binary optimizer has been upstream into the LVM project these days. And these are all open source. And if people are interested in collaborating or doing projects, improving on top of them, you're more than welcome. And that concludes my talk. And a bunch of the papers that I mentioned there, they're all available in my website listed here. And if you have questions also, I have to take them here, or you can reach out to me later. That's all I have.
Question, folks. Guilherme.
I have a question. I worked at Meta during May and June for this year.
You did? Okay.
Yeah, but I haven't worked in Hack Compiler. I actually met an intern that was working there.
Mm.
And I actually coded Hack for doing some main points and kind of stuff. And I actually find out that, okay, Hack is a pretty cool language, so it's pretty mature. So it's kind of, oh, PHP, this is not.
That's the pre-concept that we have to try to overcome.
Definitely. But, and I know that it's performance-wise, as you showed, is very good.
Yeah.
But compared like to other languages, I know that the ecosystem of them are better. Like, I tend to compare with Java, an example. Like we have a lot of libraries in Java that if you're building a web server, it seems to me that Java is a better choice. Like compared to Java performance-wise, do you think that Hack is better because of the compiler? Because it seems pretty close.
Yeah, I suspect it's probably pretty close these days. It's very hard to measure because we don't have like any real application written in both languages that we can compare performance. And in terms of libraries, yeah, I think it goes by personal preference and what people have experience dealing with. I think a lot of people like a lot, and kind of what we have in Hack is that, especially inside the company, there's a lot of libraries and things that we use that are make it very easy and people are very productive. And it's kind of considered to be the high standards inside the company that we try to match for other things, people writing code in Python and other things. And even people in Java, it's funny, when I gave the last talk about Jumpstart at the conference last year, one of the questions I got at the end was from someone working with Java asking, when are you bringing this to Java? Because Java warm-up is really bad. We need something like that. So, yeah, I think for a long time, I think the JVM was kind of the golden standard that we tried to build for Hack. But I think these days it's pretty comparable. Yeah, some are better in some areas, but Java is better in others. You have questions?
Just ask about the infrastructure that you built HHVM upon. It was only LLVM, or did you build something from scratch?
It's built from scratch. It's not based on LLVM.
It's not because you mentioned LLVM.
Yeah, we use LLVM just for the boat project. HHVM is something we built from scratch, and we actually, it's funny, for a while we thought we built a very simple backend and started optimizing on top of it, and at some point we decided, okay, maybe we should use LLVM, but people say it's very slow, so we were a bit concerned. We actually had some 3 people working on a LVM-based backend for HHVM, and they built and got that working. And not surprisingly, it was 100 times slower to compile the code. So we thought it was going to be slower, but it was very slow. What was even more surprising is that even if we ignored the compilation overhead, the performance of the JIT code in the end was worse than what we had with our custom backend. So we ended up just dropping that completely.
Comparing with the JIT for LLVM.
Comparing with the JIT for LLVM.
Yeah,
so
I don't think they have much people working on the JIT for LLVM actually, because I have a student work with it nowadays, and he has been surprised with some lack of features there.
Yeah, and I think also what some people, we had people from Apple talk to visit us, and we showed them code that was being generated, pointed them lots of problems in register locator and other things, and they told us, yeah, I think the code you have with all these dynamic type checks and things is very different from what we built to the compiler. It's not coming like a nice C code that's well typed. And it imposed a lot of challenges, a lot of things there that they thought, yeah, this would be very hard to fix and stuff. And for us, internally, we had agreed that, okay, this has to be a decent performance win for us to justify moving over to it, because we're not just building the system, we're maintaining this running in production. So we're going to add a big dependence on LVM, and we thought, okay, it better be like a 3 or 5% win at least to make us consider. And surprisingly, even if we ignore all the compilation overheads, it couldn't beat our backend, and so we dropped that at some point.
Following up on that question, at some point, I think it was when you were talking about HF sort, you talked about how GCC was ordering the sections. So you just said you don't have a dependency on LLVM, but you are using GCC for something inside HHVM.
So HHVM is written in C++, so that's compiled with GCC.
Okay.
So part of the runtime, and also people get surprised because HHVM is a JIT compiler, but actually spends more time in code compiled with GCC, or these days we switch to use Clang, because there's a lot of things that are just inefficient to generate JIT code all the time. So if you're doing string concatenation or any array access in PHP is actually a hash table lookup, and you don't want to expand every array access to be an inline hash table lookup, because that's going to bloat the code too much. So all of these things are very carefully written code in C++, or sometimes even in assembly that we call from the JIT code. So we spend a lot of time in this code, even with the JIT.
Question, folks?
Is not experimenting with ARM builds, like for the HHVM?
ARM?
Yeah, because I know that Amazon is kind of experimenting that in the cloud, and it's kind of promoting, oh, we have an ARM processor, and I know Meta has their own data servers. I don't know, like, they change the hardware as fast as it was, but are you guys experimenting?
Yeah, we're doing some work evaluating ARM as well. Yeah, we have a backend for HHVM that was written by ARM vendors that wanted to sell us chips. We told them, okay, we need to be able to assess the performance in there, and we're not spending engineering effort to build an ARM backend, so they actually built an ARM backend for us, and what we are using. And similar thing happened with IBM, trying to convince us to build a PowerPC backend. And it's funny because we told them the same thing. Okay, you guys are welcome to build, and they hired Instituto Eldorado here to build a PowerPC backend for HHVM years ago. So that was funny because I also worked at Instituto Eldorado before I moved.
There's an increase of performance between this architecture? Is there like an increase of performance?
In performance, we never evaluated it. It's too early to say anything. We're just starting to look at ARM at this point. So, and PowerPC.
Thank you.
Question, folks? No? I have a question, Guilherme.
Yeah.
You mentioned about HHVM, that you had some power counters measurements there. Did some of those counters kind of really help in terms of putting the region together? Or some specific counters which were really helpful?
For forming regions, basically we look at the hotness of each of those blocks. It's just basically a counter how many times we executed this and that, so we know this is the most common path. I'm going to build a region including these, and if there's some path that's rare and you don't want to include in the region because it's customized, we leave that aside. But it's basically just the execution counters. We don't use any hardware counters to measure cache needs or anything like that for that purpose.
So the hack language is widely available and open source, and it is really used internally at Meta. Is it also used in all those other PHP websites that you showed there, or some other project from outside of Meta?
Yeah. Hack these days, it's used by a few other companies, not many. Unfortunately, I wish there was more. The biggest user outside of Meta is Slack. It's written in Hack and runs on top of HHVM also. And for a while, we had other websites running on top of HHVM, including Wikipedia, Baidu, from that list. And for some time, we kept HHVM running, being compatible with PHP and also supporting Hack as before. But at some point, that became a lot of maintenance for us, and we had to decide what we do, and we split, we forked from PHP, because PHP was adding features, we were adding other features. We didn't really have resources and didn't have much code written in PHP that we cared and wanted to support. So I think it was about 4 years ago, we dropped support for PHP. That was a bit unfortunate for the project, in the sense that we lost, Wikipedia went back to run on top of PHP, for example, and I cannot claim it runs on top of the virtual machine I built, unfortunately. But it was the right thing to do for the company, because it allowed us to evolve much more quickly without having to work with other committees and people trying to argue what features should go in and should go out, and things like that.
Ok, já.
Primeiro, Guilherme, obrigada pela palestra, foi ótimo. É uma curiosidade, não é uma pergunta técnica. Eu vi que você mostrou um dos gráficos uma foto, que acho que é o grupo que trabalha contigo.
Sim.
E aí eu fiquei curiosa de saber como que é o background desse grupo, porque eu sei que você tem um background bem forte de compiladores, de arquitetura, né? Todo mundo com esse background, ou tem pessoal mais também de sistemas distribuídos?
No meu grupo, pessoal, boa parte tem mais experiência com compiladores, mas não todo mundo. Tem gente que só é boa de sistemas em geral e que vem e que trabalha. É bem diverso, assim, o grupo. A maioria do pessoal não tem doutorado, assim, tem gente que tem especialização, mas não tem doutorado, assim, em compiladores. Mas é bem diverso. Tem gente com todos os níveis de experiência. Essa foto que eu gosto de mostrar, isso é o grupo, na verdade, isso já tem quase 10 anos, o dia que nós lançamos a HHVM para rodar o site, botando em produção. Veio o Marcos Zuckerberg,
o CTO da empresa, daquele cara do meio lá.
Veio todo mundo lá celebrar com a gente, lá, de lá, que a gente tinha passando 3 anos construído o sistema e estava finalmente botando em produção.
Legal, parabéns.
Legal.
Bom, agora que a gente mudou para português, né? Uma última pergunta para você, Guilherme. Essa sua curva vem crescendo aí praticamente linearmente e com o mesmo coeficiente angular desde janeiro de 2013, né? Quer dizer, vai completar aí 10 anos ano que vem, ela está crescendo aí. O que você está imaginando que vem ali depois? O que você está apostando em termos de técnicas para otimizar?
Tá ficando mais difícil de otimizar o sistema. Tem muita coisa que muda, né, no ambiente. Como eu disse, a aplicação em si está evoluindo, a gente está toda hora trabalhando, acrescenta features novas, o pessoal começa a usar, a gente otimiza mais ela, tem feature que a gente acrescenta que o pessoal não usa, então a gente não gasta tempo. Então sempre tem essas coisas mudando, tem hardware mudando, tem outras arquiteturas, às vezes, que pode trazer ganhos, tem features novas que o pessoal coloca, que a gente se vale, mas não vai... Eu comentei um dos colegas que eu acho que até está nessa foto, tá, esse cara bem à esquerda aqui, na jaqueta vermelha, ele é um dos caras que escreveu a HHVM original, e a Hotspot. E eu comentei, ele já aposentou isso aí depois, alguns anos atrás, eu comentei com ele, Chico fazendo isso, e ele falou, pela minha experiência com Java, isso aí deve ficar uns 20 anos fazendo. Então acho que ainda tem mais uns 10 anos.
Legal, tá joia. Bom, vamos agradecer o pessoal, então, a palestra do Guilherme. Obrigado, Guilherme.
Aqui não.